Today, we're going to talk about the hidden logic behind our most critical infrastructure. Things like the internet, the power grid. It's a concept called a minimum spanning tree, and it's so much more than just another algorithm. It's really the blueprint for building efficient networks. So let's dive in.
So, when you think about optimization, your mind probably jumps to something like Google Maps or a GPS, right? Or always trying to find the fastest, shortest route from point A to point B. And that's the world of shortest path algorithms. But what if the question isn't about just one trip? What if you're the one who has to actually build the roads in the first place? That's where minimum spanning trees, or MSTs, come in. They tackle this much bigger, more fundamental problem. How do we connect all the points using the least amount of material, the lowest possible cost? Period. And this right here, this gets to the absolute heart of it. This is the key difference we're exploring. It's using the map versus designing the actual city grid. One optimizes a single journey, the other optimizes the entire system's foundation. So here's our game plan for today. First, we're going to lay down the basic rules of efficiency. Then, we'll look at two different blueprints for getting the job done. One we'll call the edge-first plan, and the other the growth plan. And finally, we'll see how engineers decide which tool is right for the job. Okay, so let's start with the absolute fundamentals. What exactly is a minimum spanning tree? What makes it tick? Okay, I know, that's a bit of a textbook definition, so let's break it down. Just imagine you have a bunch of points you need to connect. Cities on a map, computers in a network, whatever. And every possible connection has a cost. A minimum spanning tree is simply the cheapest possible set of connections you can pick that links up every single point without creating any wasteful redundant loops. So this leads to two golden rules. First, everybody has to be connected. You can't leave any nodes isolated. Second, and this is the really important part, there can't be any cycles, no closed loops. Why? Well, because a loop means you have a redundant connection. It's an extra road you didn't need to build. An MST is perfectly efficient. It has just enough edges to connect everything and not a single one more. All right, this is absolutely crucial. This is the number one thing people get wrong, so let's be super clear. An MST does not find the shortest path between any two specific points. In a city designed with an MST, the drive from your house to the grocery store might actually be a little longer. Why? Because the goal wasn't to optimize your trip. It was to minimize the total amount of asphalt used for the entire city. It's all about the global cost, not your local convenience. And this isn't just theory, okay? This is literally how the modern world is built. We're talking about laying fiber optic cables across the ocean, designing a country's power grid, or wiring up servers in a massive data center. These are all incredibly expensive projects where the goal is exactly the same: connect everything with the absolute minimum cost. They are all real-world MST problems. And this quote just nails the engineering mindset behind it all. In any system where every connection costs real money, materials, or energy, any kind of redundancy, a cycle in our graph, isn't a cool feature. It's a bug. It's a costly liability. MSTs give us the blueprint to eliminate that waste. All right, so we get what an MST is and why it's so important. The next question is, how do we actually find one? So let's look at our first blueprint, Kruskal's algorithm, which takes what I like to call an edge-first approach. If you only remember one thing about Kruskal's, make it this. It's a super simple, greedy strategy. You always add the next cheapest connection you can find, as long as it's safe, and by safe, we just mean it doesn't create one of those wasteful loops. So here's how it works step by step. First, you take every single possible connection in the network, throw them all in one big list, and sort them from cheapest to most expensive. Then, you just work your way down the list. Grab the cheapest edge. Ask yourself, does this form a cycle with what I've already picked? If the answer is no, great, it's in, you keep it. Then you grab the next cheapest one. Does this one form a cycle? If yes, you just throw it away and move on. You just repeat that simple check over and over until everything is connected. Now you might be wondering how it checks for cycles so quickly. It uses a really clever tool called a union find data structure. You can just think of it as a super fast way to ask, hey, are these 2 points already connected to each other somehow in the tree I'm building? If they are, adding another link between them would obviously create a cycle. This simple trick makes Kruskal's algorithm really intuitive and incredibly fast for what we call sparse networks, like connecting cities that are spread far apart. Okay, so that was the edge-first plan, where we look at all the edges at once. Now let's check out a completely different strategy. This is Prim's algorithm, and it doesn't look at a big list of edges. Instead, it thinks more like a gardener. It starts with a single seed and grows a perfect tree, one branch at a time. The mental model for prims is just as simple and elegant. You are always trying to expand the frontier of your current tree in the cheapest way possible. It's kind of like watching a crystal grow outward.
So here's the growth plan in action. You start anywhere, just pick a random node to be your seed. Now you look at all the possible connections that reach out from that single starting point, and you pick the absolute cheapest one that connects to a new unvisited node. Bam, you add it, and now your tree has 2 nodes. Then you just repeat the process. From this bigger tree, you ask again, what's the single cheapest connection from anywhere inside my tree to the outside world? You find it, you add it, and you just keep growing like that until every single node is part of your network. And to efficiently keep track of that cheapest next step, Prims uses a tool called a priority queue. Just think of it like a smart to-do list that automatically keeps the cheapest, most urgent item right at the top for you. This makes it lightning fast for really dense crafts where there are tons of connections to think about. And if that whole grow the frontier idea sounds familiar, it should. It's the same basic engine that powers Dijkstra's algorithm for finding shortest paths.
Okay, so we've got 2 totally different blueprints, Kruskal's and Prim's, that both produce a perfect minimum spanning tree. So how does an engineer choose between them? And where does all this fit in the grand scheme of graph theory?
And this is the classic engineering question, right? You have 2 completely valid tools that both achieve the exact same optimal result. So how do you decide which one to pull out of the toolbox? Well, the choice really comes down to the graph's density. Kruskal's, which starts by sorting all the edges, is perfect for sparse graphs. Think connecting a few cities with only a handful of roads between them. But Prim's, which grows outward from a single point, is much faster on dense graphs, where everything is highly interconnected, like the circuits on a computer chip. So different tools, different strategies, but they both arrive at that same perfectly optimized structure.
Now let's just zoom out for a second and see the big picture. You have algorithms like breadth-first and depth-first search, which just tell you if you can get from A to B. Then you have Dijkstra, which finds the single best route. But Kruskal and Prim, they're in a class of their own. They're not concerned with routes at all. They're about designing the entire network for maximum efficiency.
And that brings us right back to our central idea for today. This is the distinction that really matters. One is for the person using the system, finding their way around. The other is for the architect, building the system, making it as lean and cost-effective as possible from the ground up. So, at the end of the day, remember this. Whether you're looking at a data network, a power grid, or even a global supply chain, the most successful and resilient systems are always built on an efficient foundation. And at the very heart of that foundation, you'll almost always find the elegant and powerful logic of the minimum spanning tree.